Hello everyone and welcome to another episode of Interstigation. In today's episode of Interstigation, finally going over 2021 AIME 2 number 15. So in this problem, it says that f of n and g of n be functions satisfying this kind of like a piecewise-ish conditional function. And g of n really similar, but we just have the numbers switched here. For positive integers n, so we only consider positive integers. So you're going to know this is some sort of combination between algebra and number theory because we're only considering positive integers n. And we want to find the least positive integer n such that this thing equates. That's very random, so let's just leave that aside for now. Let's think about how can we decode what these functions are actually saying. So it seems like we are really focusing on perfect square numbers, perfect square integers, those integers that are squares of other integers. So let's say like 7 squared is 49, so 49 is a perfect square. You all should know this. And let's draw a number line. Start with 1 because we don't really care about 0. The next perfect square is going to be 4. Let's draw this a little bit closer. 4. All right. 1, 2, 3, 4, 5, 9, 16. It's not really to scale, but it works for now. So if our n is one of those perfect square numbers, then the output will just be square root of n. If it's not, let's say, what if our input n is like over here, then what it will do is I add 1 to the output while just taking the input of f of n plus 1. So we increment 1 on the number line while adding 1 to like our kind of output counter here. So 1, it's still not a perfect square. We add another 1. It's still not a perfect square. We add another 1, so we are here. Now it is a perfect square. So now we are going to have square root of 9. So we started with 6, we added 3, and now we landed with 9. Now let's say at some point, let's just go with an arbitrary, let's say here are 3 perfect squares. Let's say k minus 1 squared, k squared, and k plus 1 squared. Let's say we have n here. So if we have n here, then for f, we would just add 1 until we get to k squared, because we add 1 each time. There's no way we're missing k squared. So our output would be this distance, how much we have added, how many 1s we have added, plus the square root of k squared. So it will be k plus this distance would just be k squared minus n. However, if we consider g is basically the same thing, but in this case, we're incrementing 2 at a time. So from here to here, 2. From here to here, 2. You notice it actually misses 9 right here. So it wouldn't terminate at 9. So it will go all the way to 16. Plus 2, plus 2, plus 2. Plus 2. And plus square root of 16 over here. And if k, so if n and k squared, let's just write it in mathematical notation. If k squared minus n is 0 mod 2, they have the same parity. This means that after some increment, this g function will actually get to k squared. This means that our output will actually just be k squared minus n divided by 2 times 2, because the distance, the times we add 2 would be k squared minus n divided by 2, but we add 2 2 each time, so we multiply by 2, and plus at the end k. If we compare that there, that is the exact same expression. So we can't really get a ratio of 4/7 unless, I guess, both of these functions return 0, which is impossible because k is a positive integer. So we have to have k. So we already eliminated that. So we have to have k squared minus n. So if k squared minus n is 1 mod 2, in other words, k squared and n are different parities, in this case, g would actually miss k squared and go all the way to k plus 1 squared. And let's say n is odd. This means that k squared is even, right? Then this means k is even, meaning k plus 1 is odd, so k plus 1 squared is odd. So n and k plus 1 are both odd, so it wouldn't miss k plus 1 squared. You can analyze similarly when n is even, k squared is odd, k is odd, k plus 1 is even, k plus 1 squared is even. So n and no matter the case, n would not miss k plus 1 squared. So the g function would actually return us, in this case, k plus 1 squared minus n plus this k plus 1 squared square rooted, so k plus 1. And now we actually want this ratio to be 4/7, so let's copy this over. So let's copy this, paste this over. Let's copy this expression, paste this over. So we want this fraction to be 4/7. Now, it's the algebra part, right? We want to expand, cross multiply, expand on both sides, plus 8k plus 4, minus 4n, if it let me, minus 4n plus 4k plus 4. And this side is 7k squared minus 7n plus 7k. And if we just order this a little bit, it's 4k squared. And actually, let's move that to the left-hand side. So it's 3k squared. That's 7n, 4n, and so let's move that to the right-hand side. That gives us 3n. So that's all taken care of. We have 8k, 4k, and 7k. That gives us a minus 5k. And this plus 4, that gives us minus 8. If we want to solve for n, right? So if we divide both sides by 3, that gives us n equals k squared minus a third of 5k plus 8. Now let's do the same analysis again. We want, or we need, k and n to be of different parity. So if k is odd, then k squared, this is odd. And we're assuming that this thing is divisible by 3. That is kind of like the start of all these things. But it wouldn't actually affect our divisibility by 2. Dividing by 3, if I have a 2 to start with, and if I divide by 3, I still end up with an integer, I will still be able to divide by 2. Because I didn't take out the factor of 2, right? So if this is odd, this whole thing is odd, so 5k plus 8 is odd, and divide by 3 has no effect, it's still odd. So odd minus odd is even. So we're fine with that case. Now, if k is even, then 5k is even, plus 8 is even, and divided by 3 has no effect on it, so it will be still even. So even minus even, it will still be even. So this case we don't want because we need n and k to be of different parities. So this case we cannot even have. Now, we just want to solve this 5k plus 8 when is this 0 mod 3? Because we have to let n to be a positive integer, right? So we want the right-hand side to be a positive integer, so 5k plus 8 must be divisible. So minus 8 on both sides, again, negative 8, which is also positive 1. 5k is 1 mod 3. And to divide, we just want to find, okay, 1 cannot divide by 5. Plus 3, 4, no. 7, no. Plus 3, 10. Now, yes, so 10 divided by 5 is 2, so k is 2 mod 3. Note here, it's still mod 3 because 3 and 5 are coprime. They're relatively prime, so the mod doesn't need to change. Now, let's take a look. We have k is 2 mod 3, and we know k is odd, so k is also, let's write this in blue, k is also 1 mod 2. If we combine these two conditions by Chinese remainder theorem, or you just bash it, like there's 6 cases, right? So that's k is 5 mod 6 if you combine these two conditions. Now let's just try. So case 1, I guess k equals 5. K equals 5. In that case, n equals 25 minus a third of 33, which is 14. Now, if we take a look at our number line, 14 is here, and there's a 16 in between, and then that's 25. We want the k to be 25, but if we input 14 here, both of the functions, this is f, and this is g, both of them would hit 16 and terminate. So we can't even have that. 14 is too small for us. So next case, k equals 11. If k equals 11, then n equals 121 minus a third of 55 plus 8, which is 63. So that's 21. That gives us 100. So 100, as you know, is exactly a perfect square, so both f and g would just terminate. Both f of 100 would just be equal to g of 100 equals to 10. And k of, let's say, is 17 now, because we need to have it always 5 mod 6. That n is equal to 17 squared, 289, minus a third of 5 times 17 plus 8. So 85 plus 8, this is 93. So minus 31, this gives us 258. Now if we draw a number line, we have 256 here, which is 16 squared, 258 here, 17 squared equals 289, and 18 squared is 324. So f would hit here, and g would hit here, just as we wanted. And if you guys wanted to check, that is fine. You can just plug it into the original equation, or this expression we have over here. But we would actually get f of 258 is 48, and g of 258 is 784, I believe. And that ratio is indeed 4:7. So our answer at the end is n equals 258. So that is the ending problem of AIME 2021. And after this problem, I will try my best to get the first few problems on the most recent AMC to upload it to you guys. I will be likely going over the 10 exam, but if you want to see the 12 exam, you can just tell me in the comment section below, and I might consider doing that. I won't be covering the A exam, just because my friend is going to be covering that shortly on their channel. If you click below in the channel description, you can find his channel as well. Without further ado, if you are watching this at the release, I wish you a Merry Christmas. But if you're not, have a great day, and I'll catch you in the next episode. Goodbye.